Hi, I'm Greg Paulsen, the Director of Application Engineering at Xometry. Today we're going to put some materials to the test. In the past we've done similar tests where we've subjected 3D printed parts to extreme conditions like high heat, torsion, and acute impact. These are great to show the maximum limits some materials can withstand, but what about when they're stressed to a part over time? A real world situation would be where parts are in a continuous movements, or even when they are being transported in a high shock environment. Think like a cargo freight or air transport. We'll simulate this situation by subjecting 9 3D printed test samples to repetitive, high-speed motion. So, will it vibe? Let's put on our safety glasses and find out.
For this vibration test, we are using an off-the-shelf Sawzall, which is a reciprocating saw providing rapid back and forth movements. We have 3D printed 9 test coupons over 5 different 3D printing processes, and we'll run them over 2 minutes. We also added a bolt to serve as additional weight, hopefully exaggerating movements during the 2-minute test. Let's take a look.
So we're gonna get started in 3, 2, 1. Ooh, very violent beginning here, boom! This is why we wear safety glasses, folks. That just launched about 6 feet. So what's interesting about this test is all these parts are going to find its resonance, which is that difference between how it's flexing, so the actual flexural modulus of the part, and just the movement of the Sawzall. They're going to find that at different times, and probably the most violent movements is happening when that Sawzall is kind of warming up. So the start and stop is actually probably the most violent flex movements of this. The test that we're doing though is about vibration. So I don't mind it actually falling into a certain level of equilibrium like you're finding right here with this kind of like X-shaped pattern that is showing up on the camera. It's more about, can it survive long-term duress? All right, so let's talk about what we just saw in this Will It Vibe test. We tested 9 materials, as well as what type of properties they exhibited. These materials were thermoplastics, like those made using SLS laser sintering or HP multi-jet fusion, as well as FDM. And then we also had these thermosets, so these materials made with stereolithography, as well as that carbon DLS process. So our thermoplastics tend to exhibit a nice flexibility to it, ductility, and that's because they're made by actually melting a plastic through and creating the form of the part. Our powder bed fusion tend to survive this test because they have a good, more isotropic result, which means regardless of direction, they have fairly uniform designs and fairly uniform mechanical properties. The thermoplastic ASA, which is built using fused deposition modeling, didn't survive as well. In fact, this actually kind of lacerated through. It likely had a little bit of a failure on one of the cross sections where this filament was moving. So you actually see it's not a clean break, it's more of a tear on the FDM part. Our thermoset materials like Accura Extreme and Accura 60 are made using stereolithography. Accura Extreme tends to have more flexibility in the way it's engineered, and I was actually very impressed that it did survive this test because a lot of times SLA is known for being more brittle. Accura 60 did shatter on us. And that's because it's more formulated to act like polycarbonate. It just ended up having a single break right at the stem, and actually as it was flying in the air, I saw a break into another piece right where that bolt was. The other thermosets that we have are actually through carbon DLS. So this process actually grows the parts by moving continuously up, giving more isotropic results. Carbon DLS's UMA, which is a single stage process, which means it is built and cured and doesn't need a post-thermal cure to it, it was actually very resilient. It's a little bit better than SLA, even that Accurate Extreme material. This proved to be a little bit more resilient to that. So UMA was a really impressive general purpose material. The epoxy material ended up failing because it is stiff. As we've seen, those flexible materials tended to survive that vibration better. The stiffer materials had a lot more to fight against. And in this case, that's exactly what happened. So a very nice, clean, glass-like break on the epoxy. And the last material that I wanted to show was that flexible polyurethane. I did not expect this to break. It is an extremely flexible material. But the flexible polyurethane is used for, say, a clasp or something with a snap clip. Sometimes it is too flexible to actually be a structural feature on a part. I was expecting it to go back and forth and kind of Woody Woodpecker on the part there, but what ended up happening was more of a hula dance where it stayed stable and moved back and forth this way. As you can see by me manipulating this, it still is a very robust material for things like shock and vibe testing. So the materials that we tested today, and even more information, is available at Xometry. We have design guides, material information, spec sheets, and we even instantly price and provide lead times for 7 different 3D printing processes right online. All you need is a 3D CAD file.